Hello everybody, my name is Evan, and welcome back to the Big Brain's COVID-19 series. Today we'll be talking about vaccines and immunity, or more specifically, what are vaccines, how are they made, and why are they so important, especially now during the COVID-19 pandemic. Let's begin. So to begin, let's talk about immune cells. So in your body, you have white blood cells that help protect you from different pathogens. Pathogens, anything that can enter your body and can cause a disease or infection or some sort of immune response. So in your body, the main immune cells that you have, the main white blood cells that you have are B cells, T cells, natural killer cells, also known as NK cells, basophils, neutrophils, and macrophages. So these are really the main white blood cells that you have in your body. And that's not saying that the other cells aren't important. Every cell in your body performs a specific function. However, I'm just saying that these 6 are your most important ones that are used in the defense of your body. All right, let's move on. So there are really 2 types of immunity. There's passive immunity, and then there's also active immunity. So, and each of these 2 immunities can be broken down further into more specific parts. So first, let's break down passive immunity. So passive immunity, the 2 parts of passive immunity are naturally acquired immunity and artificially acquired immunity. Naturally acquired and artificially. Natural and artificially acquired immunities. So an example of a naturally acquired passive immunity would be, let me just switch colors, would be the placenta. The placenta is the organ in the mother that supplies the embryo with all of its vital necessities, such as food, water, and oxygen through the umbilical cord. And also carbon dioxide is taken out. So the placenta naturally allows the baby to have what are called IgG. So IgG stands for immunoglobulin G, which is a type of immunoglobulin that's found in your body. Another type of natural passive immunity is breast milk. So breast milk, when the baby is born, the mother lactates or produces breast milk. In this breast milk, there's an immunoglobulin called IgA. IgA is found in breast milk and gives the baby, the newly born baby, immunity, some immunity from the mother to the child. So that would be naturally acquired passive immunity. An artificially acquired passive immunity, an example would be an antivenom. Now, this antivenom could be either to like a snake bite, a poisonous spider bite, or something along those lines, with something involving venom that has gotten into your bloodstream. So the reason why an antivenom would be artificially acquired passive immunity is because the antivenom already contains the antibodies to mark and destroy the venom. Your body does not produce your body doesn't produce any antibodies or any immune responses to destroy the venom. The antivenom has everything associated with it, and then it's given to your body, and your body is able to react to it and essentially kill the venom and get it out of your bloodstream so it doesn't cause any further harm to you. The other type of immunity we have is active immunity. So again, like passive immunity, the 2 types are naturally acquired and artificially acquired. So in naturally acquired active immunity, that the one example of that is an infection. Is any sort of infection, bacterial infection, especially a bacterial infection, a viral infection, a fungus, any sort of infection is a sort of natural active immunity. In active immunity, your body is, for lack of a better word, is actively trying to fight the pathogen, is actively trying to get your body to a state of homeostasis again. Homeostasis is, you can think of it as like the perfect state that your body wants to be in, where everything is balanced. An infection forces your body to create antibodies to fight that specific infection, fight that specific pathogen. So that would be an example of natural active immunity. Artificial active immunity would be, a prime example would be a vaccine. A vaccine is a prime example of artificial active immunity because it introduces a pathogen into your bloodstream. It introduces, let's say the flu vaccine. It introduces some influenza into your bloodstream. And then, now, obviously, this flu, the viruses are severely weakened, so they don't cause any real harm to you. However, this vaccine forces your body to produce antibodies. It forces your body to produce antibodies to fight off the influenza. Now, you didn't get this yourself; you had it put inside of your body, so that is why it's artificial active immunity. And then going off of that, another example would be a booster shot. A booster shot, for example, a disease like tetanus, that would also be artificial active immunity because your body itself is producing antibodies. So now let's go on to herd immunity. So herd immunity is the reason why vaccines are so important and the reason why they do actually work. So let me give you the scenario. So let's say this is a population of people. So we have 15 people in this population. You can count them out, but there are 15 people in this population. Let's say that nobody gets in and nobody leaves this population, and then there's no movement of any sort in this population. So this population stays still. There's 15 people right now, and at the end, there will still be 15 people. So let's say that this person right here, let's say they contract whatever disease. Let's say COVID. Let's say this person contracts COVID-19. Now, assuming that there's no vaccines, assuming that there's nothing to prevent the spread of COVID, this person they could give it to this person, this person, them, and then later on they would be infected, and then they would give it to other people. Now, so this is what would, and then eventually all 15 people in this population would be affected with COVID or whatever disease. So that would be in a situation where there's absolutely zero immunity. There's zero immunity protecting anybody. So then the disease is allowed to run its course. So let me just erase that. Okay. So how herd immunity works is, let's say 5 people are given the vaccine. Let's say healthcare workers come to this community. They're in full hazmat suits, full protection, PPE, personal protective equipment. Let's say they give 5 people the vaccine. So this person, 3, 4, and 5. Let's say that. So now in this community, we have one person who has the disease, who is affected with it currently, and then we have 5 people who have been vaccinated for it, who have immunity towards the specific disease. So now let's see where the infected individual can spread the disease. So this person can spread to them, and then you go behind, and then go like that. So now you can see that there's only 5 possible people that this disease can spread to. due to vaccinations. Because these people have been vaccinated, they will no longer be affected by this disease, or if they do, it's going to be very, very mild symptoms. So now let me erase everything and let's go back again. Okay, so now after a week, 5 people have the vaccine and 1 person still affected. Let's say that another week passes and that this person, our previously affected individual, spreads it to this person. So then let me draw line transmission. Let's say that happens. But then let's also say that more vaccine doses become available. So then more healthcare workers come and then they give the vaccine to more people. Let's say this person gets the vaccine. Let's say 3 more people. 1, 2, and 3. Let's say this happens. So now in this population, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 people who have been vaccinated and have immunity for the disease, and 2 people who do not, who are currently affected. So now, how many people do you think can get the disease now? Assuming that there's no movement of people. Why don't you take a second to think about that? Okay. Now, after these 8 people have been vaccinated for the disease, there are minimal, if any, other people in this population who can be affected. And I know you're going to say, "Oh, what about this person right here? There's an open path there, and this person's not affected." Well, and also this person. While yes, you're correct. You can go that way. That's only going to be 2. That's only going to be 2 people. 2 people. The rate at which people can be vaccinated is much higher compared to the rate at which a disease can spread throughout a given population. So let's just say they are affected, but then let's say the remaining people get vaccines or get some sort of immunity. So now, what do we see in the population? We see 4 people who have the disease who are currently affected, and then we have 11 people who have been vaccinated. Now, when you look at this entirely, this population entirely, and when you compare it to when we started, there was 1 person affected, and there was nobody vaccinated. So the disease was able to spread wherever it wanted to. However, now with these 11 people who are vaccinated or have immunity, there is minimal space where the disease can spread. And if these people are young, if they even if they're middle aged in their 40s and 50s, their immune systems are going to be so much better than if it was an elderly person, an immunocompromised person, or a child in this population. So, and this is the reason why herd immunity is so needed. It's so necessary to prevent the spread of not only COVID-19, but also so many other diseases. When you look at herd immunity, yes, there will be some people who are affected, but as those people get better, as more people get vaccines, as people are moving out of infected areas and quarantining themselves, as they take measures to prevent themselves, this is how the spread of disease is limited, through herd immunity. As people get more vaccinated, there's less space, not really space, but there's less people for the disease to spread. And then this is how a disease dies off in a population. And this is the reason why herd immunity is so important. And this is why not only the United States government, but also countries all across the world, France, Britain, Australia, this is why those governments and those health services are trying to get these vaccines out to people as quickly as possible, in order to make sure that herd immunity does occur and then which will limit the spread, which will then eventually kill the virus in the long run, or whatever pathogen there is. And herd immunity, the immunity doesn't even have to be from vaccines. It could just be from an infected individual who has recovered, and now they have antibodies for this specific disease. So then that could also be another way herd immunity could work inside a given population. But overall, what you need to know is that herd immunity is of the utmost importance right now during the COVID-19 pandemic. COVID is an upper respiratory disease and can spread very easily. But as we self-quarantine, as we have more access to vaccines, as we take these safety precautions, this is how we can limit the spread. And also, this is how we can defeat the virus in the future. So now after talking about immunity, let's talk about how vaccines work. So there's really 3 main steps to a vaccine. So the first step is that weakened or dead bacteria or whatever pathogen. It could be a virus, it could be any of those. Weakened or dead pathogens are introduced in the patient, and they could be introduced in a multitude of ways. So they could be introduced through an injection, through a hypodermic needle in the arm. That's usually the most common way that you see. It could be done by that, or it could also be done orally. It could be done orally through through drops, similar to like eye drops. It can also be administered orally through the mouth. So that's how you get the bacteria inside of the patient or whatever pathogen. After the pathogen is inside of the patient, these white blood cells, represented by these white circles, are a trigger and produce antibodies to fight the disease. And I've circled here, but this red circle, and the inside you see like a green Y structure. Looks like a tree, maybe. It looks like a Y. These are called antibodies. These are what your immune cells, what they produce, and this is what your body uses to basically recognize the infection, recognize the pathogen, and how best to defeat the pathogen. So these are white blood cells, and then the antibodies. So then these antibodies stay around in your bloodstream. They stay around, and then if you have any further infections, or if you come across a live version or an unweakened version, these antibodies can quickly neutralize the invading pathogens. And most of the time, you won't even know that you've been infected. And even if you do know that you've been infected, it will be a very mild symptoms. So it wouldn't seem like much. So this is how vaccines work inside of the human body. So here you can see the creation process of a specific vaccine. So on the left, we have the beginning of the creation, and on the right, we have when basically up to the point when it's ready for public use. So let's start from left to right. And then on the bottom here, you can see the timelines of when it normally takes, how long it normally takes for a vaccine to be developed. So normally, a pathogen is discovered. In this case, COVID-19. The pathogen is discovered to be transmissible, and it poses a major threat to public health. Then, scientists or companies or laboratories, they go into the preclinical stage. The preclinical stage, they basically see what does the pathogen do to the cell, and people brainstorm about what are the best ways to not only kill the pathogen but also to prevent further infections. So after they do all that preliminary research, they go into what's called the manufacturing development. Manufacturing development is when companies are actually developing and making a vaccine. So this is through mathematical formulas. This is through biomedical engineering. This is through what you've seen in the news about vaccines months ago on the news. You've probably seen this before. and then this is how vaccines are created. And then after that, you go into clinical assay optimization, which is basically, do the antibodies work? And to put it in simple terms. After that, so that stage takes about anywhere from 3 to 8 years in a normal setting. Now, this is not COVID. COVID vaccine took, I think, a year, probably less than that to make. So this is a normal vaccine. After that, you go into phase 1. So now you're going into safety. After developing a vaccine, the thing that should be of the utmost concern is safety to human beings. While yes, your vaccine may work, if it harms the host in major ways because of the vaccine, that's not going to be an effective vaccine. So phase 1 safety. So usually this is done with 10 to 20 people. And then this is how companies really manage and monitor what's the best dosage, how often should this dosage be given, who has the best reaction to the vaccine. So that's what is done in phase 1. And similarly, phase 2 and also phase 3. Phase 3 are large-scale medical trials, and they're done for safety and efficiency. And this entirely of all the testing can take anywhere from 2 to 10 years, which it's a pretty long time for one vaccine. After that, it's the regulatory review. The regulatory review, everything, at least in the United States, all drugs that have the possibility to be administered to humans are reviewed very closely by the FDA, the Food and Drug Administration. If the FDA approves, then this vaccine or whatever drug, it can go into circulation. So this usually takes about maybe 1 to 2 years. So you can see, while the creation of vaccine, it may sound simple, the time it takes for each of these steps is enormous. And the COVID vaccine, it's a testament to how technology has really developed and how quickly a vaccine can be developed. And right now, the success rate is pretty high. So that just shows how necessary this vaccine is. So finally, let's talk about how the vaccines compare. So right now, there's many different vaccines out there, but the two most common ones that you probably either seen or heard about on the news are the Pfizer COVID-19 vaccine, and Moderna. Pfizer and Moderna are both biotech companies, and they both developed a COVID-19 vaccine that was approved by the FDA. So both of these are mRNA vaccines. So RNA is a type of nucleic acid, which is utilized by your cells to create proteins. And then, so you can see here the differences between these two vaccines. You can see how many doses each patient should get, approximately how effective they are, and then we can also see storage. We call it the storage temperature, with the Pfizer vaccine being at negative 75 degrees Celsius and Moderna being at negative 20 degrees Celsius. And then you can compare that to these vaccines, the flu vaccine and the MMR vaccine, which stands for measles, mumps, and rubella. So you can see, while a vaccine may do the same purpose, it has different ways to do that. For everyone who develops a vaccine, there's always going to be differences in how that vaccine is developed, how it's stored, how research is done, and all of that. But overall, these vaccines have shown to be immensely successful, especially in the United States. Before, just a few months ago, the United States was getting over 200,000 cases, 200,000 reported cases. And now, after the administering of these vaccines, it's dropped to below 100,000 or even below every single day. So, which is a testament to what these vaccines can do and how well they can do them. Well, that's it for today. If you have any further questions on vaccines, please look towards the Centers for Disease Control and Prevention website to answer any questions that you may have. Thank you, and I'll see you on the next episode.